So good afternoon, good morning, and good evening, everybody. My name is Nicola Draghi, and I will be guiding you through the coal and coal product statistics presentation, which was prepared by my colleague Laura and me. As Aidan already kindly remember, for the question, we will have a dedicated time at the end, but I really encourage you to pose any question if that's something really important that it's preventing you from understanding the rest of the presentation, all through raising your hands or in the chat where Laura will help me to reply to those. So let's start with the key coal trends, a review of the sector. And let's see how coal compares globally to the other energy sources. On the left side, you see that coal is the second largest source of primary energy, with a share of about 27%, just ahead of natural gas and behind oil. If we speak only about electricity instead, we have that coal is by far, I would say, the largest source of electricity generation, with 38%, again in front of natural gas. You can see here that the share between total energy supply of coal and world electricity generation is different because we are speaking of two different products, and electricity is only a portion of the total energy supply. Now, these figures come from the Coal Information 2020, which is a publication that is available on the website, was published last summer. And among the other things, we have some figures and historical trends of coal production, trade, and consumption, and also projections for 2019 data. So here on the left side, you can see world coal production trend and also some specific trends of the biggest countries, I would say. We can see that coal has been flat, coal production has been flat during the 90s, then had a speedy growth in the first decade of the 21st century, quite following the same trend of the biggest producer, which is People's Republic of China. Then again, it plateauing around 2010 for some years, to even decrease in 2016, and then recover a little bit. On the right side, you can see the rank of the biggest producer. We have China by far being the biggest, followed by India and United States. Then OECD as an aggregate, it's in the second position, but his production, as you can see, again on the left side with the dark blue line, is slightly decreasing across time. Now we move to coal consumption. I want to show you, to make you notice first, that the unit of measure is different. It's MTCE, which stands for megaton of coal equivalent, while before it was just megaton. Anyway, apart the unit of measure, we can see that, of course, the trend is exactly the same, with a flat phase during the 90s, again, a speedy growth, and then again, a plateau decrease, and so on. From this graph, we can see that the main producers are also the main consumers in 2019, but also in previous years. That's the case of China, which alone consume almost half of the global consumption, and followed by India and United States. Instead, OECD countries and United States among those see a more marked decrease of consumption compared to production. Unlike production, consumption, so at least we predicted last summer that consumption would decline a little bit in 2019. So let's give a better look at this drop. Here you see that the decrease in consumption in US and EU28 has not been counterbalanced by the increase in Asian countries, namely Indonesia, People's Republic of China, and Vietnam. We cannot see India change here because its magnitude is really small, so it's not possible to visualize that. But actually, for the first time in 3 decades, we predicted a small decrease in coal consumption by India. Now, for the drivers of these movements, we can say that in some countries, we have the transition to less carbon-intensive technology, especially for power generation, due to pollution and environmental concern. While for other countries, especially the one where energy is growing still very rapidly, we still have that coal is a really accessible and cheap source of electricity generation. Now, in which sectors is an activity is coal consumed? Of course, the exact breakdown changes between different regions in the world, but we see some general patterns, as the fact that the vast majority of coal is consumed in electricity and heat, so in the power sector, about 2/3 of total coal consumption. The rest is mostly consumed in industry, and about this, iron and steel is the most important sector within industry. And we will see more in details the explanation about iron and steel processes in the presentation. Now, back to coal exports. We see this time that OECD is, in aggregate, the biggest exporter in 2019, thanks mostly to Australia, while Indonesia in recent time has really, in the last 2 decades, has really increased its exports and has also surpassed Australia to be in first place. Then the podium is completed by Russian Federation, and we can see that coal exports in general are very polarized in the sense that 3/4 of the total exports are due to the first 3 countries. Regarding imports, we have again China being at the top with about 300 megaton, but still this is a really small portion of total consumption of China, about 8%. Then we have India and Japan. OECD as an aggregate is the biggest importer of coal, especially because of Japan and Korea, so its Asian countries, members. And we can see that Japan and Korea have a steady increase over time, while India and China had really an explosion of imports after around 2000. Now, after this review of the sector, let's move to the key concepts and start with the product classification. Here you can see 5 primary coal products, which are characterized by different chemical and physical characteristics, which also determine their uses and their price. In general, the higher the carbon content, the higher the quality. And also higher rank coals have lower levels of volatile matter and of moisture. From the left side, you see that the first 3 types of primary coal, I'm speaking about coking coal, anthracite, and other bituminous coal, are named hard coal, and those are the ones with a calorific value higher than 24,000 kilojoule over kilogram. Then we have brown coal, which includes subbituminous coal and lignite. Here, about the inclusion of subbituminous coal in brown coal, there can be different view, let's say, but we follow the one of IRES, of the International Recommendation for Energy Statistics of United Nations. And as you can see, the calorific value is lower, about 24,000, less than 24,000 kilojoule per kilogram, and for lignite, even lower, below 20,000. However, on the right side, you can see that primary coal can be classified also according to its use. So first, we have metallurgic coal, which is coking coal, which is the only one who has the right characteristics, in particular caking ability, to be used in iron and steel industry. Then we have steam coal, and that's anthracite, other bituminous coal, and subbituminous coal. That is called in this way because it's used mostly for electricity and heat generation. So it's called thermal or steam or thermal coal. And then we have lignite, which has a different classification, but can be used also for electricity and heat generation. Now, coming back a little bit to steam coal, of course, that can be used also for other application in industry and residential. However, until now, we only talked about coal, but in this presentation and also in the annual questionnaire, we actually collect data on a broader concept, which is the one of solid fossil fuels and manufactured gases. So here you have a more comprehensive list of the products that we consider. On the left side, there are still the 5 types of primary coal which we have seen before. And in addition, we have also peat and oil shale. Peat is a resembles soils and comes from decayed vegetable or organic matter, while oil shale is a sedimentary rock from which you can derive oil indeed, or you can simply use it, burn it, and use it for energy. Then they're called primary products in general, so primary fossil fuels, solid fossil fuels in this case, because this can be found directly in nature, differently from derived fuels on the second and the third column. So there are 6 derived solid products. In actually, coal tar is a liquid, so let's say 5 + 1, and 4 types of derived manufacturing gases. So all these derived products indeed comes from the transformation of primary products or from or some processing of primary products. Here we have a big scheme that I would like to guide you through. And it's very important, not only because there is the same list of products that we saw below with the same order. Column on the left is the one with primary products, then derived solid and coal tar, so liquid products, and then the gases. But it's very important here to see the interconnection between the products. So I will take the pointer and help you, starting from the top and from anthracite and other bituminous coal, which can be transformed into patent fuels. And patent fuels indeed is manufactured from the fines of anthracite and other bituminous coal with the addition of a binding agent. Then still especially from other bituminous coal, I would say, we have the production of gas coke, which is used for the production of town gas. Town gas now it's no more very much used because it has been substituted by natural gas. It was much more used some decades ago. Anyway, gas coke is used for heating purpose. And in the same way, we have gas work gas, which is a gaseous product. Very importantly, from coking coal, we have in orange all the products related to iron and steel. So first, from coking coal, which is used in coke oven, we have the production of coke oven coke, coal tar, and coke oven gas. Then further, coke oven coke used in blast furnaces produces blast furnace gas. Then we have other recovered gases which come from further processes of the iron and steel industry, where not necessarily there are energy products, but sometimes in the output there are these gases which indeed are energy products, have some energy content and can be used for energy purposes. Then at the bottom, we have BKB and peat products, which are basically BKB is briquettes, peat products is peat briquettes, and they are produced in a similar fashion than patent fuels from anthracite and other bituminous coal, peat products and BKB from brown coal and peat. So I hope that this is a little bit more clear. Of course, take your time also to look at it after the presentation. So now let's move to the next slide. And let's dive into the coal balance. So this is a simplified flowchart. We start to the left, and the left side is the supply, while the right side is the demand. In the supply, we start from production. Production can happen from surface mines or from underground mines. But also, we saw from the previous slide that there are many derived coal products which come from transformation. Then we can have also some production of some coal products coming from other sources. This is the case when we speak about wastes, so coal can be recovered from some waste piles, some slurries, but also from some questionnaire. So in some questionnaire, a product can be produced, but then it's consumed in the coal questionnaire, and then we have to report it in production also in the coal questionnaire. To give you an example, there are some petroleum products which can be added to coal or peat briquettes as binding agent, increasing also the calorific value. And in that case, we put it in the production of briquettes from other sources, and in particular from oil. Then we have, very important, we pass to trade, so to imports and exports of coal, and then to stock drawing or stock building. Very importantly, imports and exports and stock change have their corresponding signs. Now, on the right side, we have demand. First, we see that there is transformation of coal products into other coal products, but also into other types of energy. That's the case of coal, which becomes electricity in power plants. Then there is energy industry home use. Here we account for coal and coal products, which are used for energy purposes to sustain energy industry activities. That can be the case of power plants, which need their own electricity to support their operation, but can be also mines which need some equipment to run, and we can use coal and coal products to make it run. Then total final consumption, that is divided in final energy consumption, where other include several sectors, among which residential, and then non-energy use, where coal is used as a feedstock in the production of a non-energy product. Then we have distribution losses that can happen during the transportation, distribution of coal, or in the case of gases, if these gases are vented. It's not written here in the slide, but when supply and demand don't match, we have a statistical difference. Let's focus on the production. There are three types of production we saw from underground, surface, and from other sources. Especially surface open cast mines are usually a little bit cheaper than underground mines, but that depends, of course, from country to country. It's very important to understand that which production to report in the questionnaire. So we consider only the amount of product which has been already cleaned, so it's ready to be sold in the market. So when from the mine a certain amount of coal is extracted, first there is a process of cleaning and removal of inert matter, and then the quantity which remains after that, it's the one to be reported in the questionnaire, and in general in any coal balance. So this amount includes also the quantity of coal which is consumed in the production process. So in the mines for heating or the operation of some equipment or auxiliaries. Now let's go to trade, which is very important because coal is a very tradable product. It's very easy to be transported over long distances with ships or with trains. So here it's very important to define the boundaries of our imports and exports flows. So for imports, we define the coal which enter a country for domestic supply, so to be used internally in the country. While for export, we define the coal which has been previously domestically produced and then leaving the country. This means that transit trade is excluded. Here below, we have some simplified scenarios where for country A and B, you can see that generally there are no problems there, especially if production is more than export. The quantity of coal produced is bigger than the quantity of coal exported. For country C, we have some problems because we have imports, we don't know still about the consumption, but we have some exports, and the exports most probably come from the imports. In that case, generally, we would be in front of transit trade. So yeah, so here there is, we would query the country and we would have a discussion with the country. So it's very important from your side to get the most accurate information about this data and then report them also to us so that we can have a discussion on where to put these questionable amounts. There are many types of transformation of coal. We saw that I quickly listed before, but the most known ones is the use of coal in electricity, heat, or combined heat and power plants to produce indeed electricity and heat. But we have also, so this is the case of transformation of coal in another form of energy, electricity and heat. But we have also the transformation of coal in other coal products. That's what happened in coke ovens, in the blast furnaces, which are all in the iron and steel sector, and where among the products we have, among the outputs, we have energy products as coke oven coke, coke oven gas, coal tar, and so on. And then we have gas works, where coal and coal products are converted in gas-work gas and gas coke. We can have, for some countries, also the conversion of coal in other energy products. That's the case of coal liquefaction plants and the conversion into oil products. Let's dive a little bit more into how a power plant works, even though I'm sure you all know about that. And you all know that coal is burned to produce heat, to heat up the water in a boiler and produce steam, which drive turbines, which then move a generator, and then electricity is produced in this way. So the average efficiency worldwide for electricity-only power plant from coal is 37%. How is that calculated? It's a ratio with at the numerator, electricity and heat, and in general, the output of the power plant. And at the denominator, the input from coal. Obviously, both the numerator and the denominator have to be in energy units because we are measuring energy. And electricity and heat, if they are measured or accounted in two different types of energy, they have, of course, to be converted into the same type. And for coal, we have calorific value to do that. Very important. Let's see an example of transformation for the iron and steel sectors and coke ovens, which is very important indeed, as I said. Basically, in coke ovens, what happens is that coking coal undergoes a carbonization process. So it's heated up in an oxygen-free atmosphere in the coke oven. And the primary output, the most important output, is the coke oven coke. But also we can have, and we surely have, other outputs, energy products, which are coke oven gas and sometimes, if recovered, coal tar. Now, these further outputs can be reinserted again, not inside the coke oven, but can be used. So reinserted is not the exact word. Can be used again within the coke oven to produce some energy. So outside the coke oven, they are burnt and produce energy to sustain their operation. The efficiency of coke oven has a range from 70 to 90% and can be calculated again with at the numerator the outputs and at the denominator, all in energy units, of course, the inputs. At the top, coke oven coke, coke oven gas, coal tar, and at the bottom, coking coal plus other inputs that can be also energy inputs. As we said, heat or electricity coming from power plants or coming from the burning of coke oven gas and coal tar. Let's zoom out and have a general look, a general picture of the iron and steel sector, which is very important for coal because there are touched a lot of flows from the balance, from the demand of the coal balance. So there is transformation, energy industrial use, and final consumption. Now, transformation, we said that many times, we say it again, is when coal or coal products is transformed into another energy product. And it happens in coke oven and blast furnace. In the same way, it can be that some of the output are used to support the operation of coke oven and blast furnaces. So in that case, we have that fuel, the fuel consumed in that way, has to be accounted under energy industry own use. Then we have, of course, several more downstream processes in the iron and steel industry, where still we need the energy, they are very energy intensive, and fuels are consumed to provide energy in those processes. In that case, we will put them in final consumption of iron and steel. Now, let's zoom in instead on this sector, let's say. And we can see first that in the darker blue arrows, we have the energy products which are used for transformation. Coking coal in the case of coke oven coke in the case of blast furnaces, but in the case of blast furnaces, we have also bituminous coal, which sometimes is inserted through the method of pulverized coal injection inside the blast furnace to improve its performances and also to reduce costs. So these are the products which are counted in transformation. Then there are some energy products which are output of this transformation. That's coal tar, that's coke oven gas, blast furnace gas, and also later on oxygen steel furnace gas. Now, but oxygen steel furnace gas, we will speak about that later. So let's focus on the one from blast furnace to the left. Now, these other energy products can be used as energy industry on use to give heat and energy in general, so also electricity, to blast furnaces and coke ovens. So they are indicated, the use in that case is indicated with the light blue arrow. In the same way, blast furnace gas could be used in later stages of final consumption of iron and steel, and that's why we have the green arrow. As you can see, I said before about oxygen steel furnace gas, and I will mention that it's usually used in final consumption because it's usually used to provide energy in basic oxygen furnaces that we do not consider in the energy industry because usually they do not involve energy products. The input is pig iron. So I want to show you that the difference between energy products, coking coal, coke oven coal, coke oven coke, and so on, with instead non-energy products. I'm speaking about iron ore and pig iron, which instead have gray arrow and don't enter the domain of energy statistics. Here in yellow again, the products which are collected in energy statistics and the efficiencies of the processes. Coke oven coke between 17 and 19, blast furnace a little bit more than 40%, while for iron and steel, we account for all the processes which are in the International Standard Industrial Classification Group 241 and Class 2431. Here you can have definitely more details about the processes which are in that class. Now, we have defined the coal product classification, see the elements of the coal balance, but let's see how in practice we translate this into data collection, data validation, and in general in the joint annual questionnaire. Data collection can happen from several sources. Surveys from supply and demand actors. So I'm speaking about mining companies, but can be also enterprises in the transformation sector, in the final consumption sector, cement manufacturers here, or directly households. Also, the data can come from administration data, ministry, energy regulators, very important customs office, which usually have the most updated data about trade. Then can come from direct measurements. That's the case, hopefully, when available, of calorific values. And then from other association, national or international, coal association, but also the World Steel Association. And related to the World Steel Association, we have also the possibility to estimate or model some products in case it's not we're not able to collect them. For example, from pig iron production, we can derive blast furnace gas production and so on. We also saw in slide, I think 15, the one with all the products, that all the products in the iron and steel industry are interconnected, so we can estimate and model one of those from the others. Here, it's the annual questionnaire. So we have four main tables. The first one is called flow, but it's nothing else that many commodity balance, one for each product, one after the other. So the column will be the product, and the flow, the consumption, will be the rows. Then we have two tables, one with imports by source, and the second with export by destination. And then a table for calorific value, where we will include all the products which have calorific value, while for the gases, we already collect these products in energy units. So the conversion has been already done, and there is no calorific value here to report. Then there are 17 products and corresponding 17 corresponding product sheets, where basically the four tables that we saw above are condensed for one product. Let's see one of the first sheet of the joint annual questionnaire, which is the menu sheet, we see on the right side, I'm going to use again the laser pointer. On the right side, we see the possibility to select table 1, 2, 3, and 4. 4 are selected here. So they give a picture of a specific year. Then we have the possibility to enter the data in time series. In the 17 product sheet, we have time series, historical time series of each flow. Then we have the possibility to transfer the data in a CSV format or other formats. Then we have the remarks sheet, very important to put some comments, and the check sheet, where we will go about remarks and check data worksheet. I will show you later on in more details. This is what we call the flow sheet. It's table 1, and as you can see, you have all this commodity balance one after the other. And on the left side, indeed, you have all the flows of the balance. At the top, the supply flows. Then we can see the transformation sector. And then at the bottom, you just can glimpse a little bit the beginning of the energy sector, industry, own use, and final consumption. For the people which are not familiar with our questionnaire, you can see a lot of cells in yellow. This means that the value has been changed in respect to the pre-filled value. So when you change a value, this is the case of 2019, but also if you do historical revision, you will see yellow cells. Then imports and exports by source, table 2 and 3. Here you can put, if you know the quantities for each country where it comes from or it's destined to. And importantly, if instead you don't know the country of destination or the source country of the product, we have a row called not elsewhere specified where you can put that amount. Calorific value table, table 4. That's very important because as you can see, the flows are reported by product, but also by flow. The calorific value are reported also by flow, which means and makes sense that production, for example, of other bituminous coal in this case is very small. Let's see if I can magnify that a moment. Production of other bituminous coal has a different calorific value of imports because, of course, it's a different type. It's the same type, but has slightly different characteristics because it comes from another country. In the same way, let me see here, you can see that in the same way for consumption, you can see that the higher rank coal, so the higher quality coal is used in industry, while a little bit lower calorific value coal can be used for other uses. And here, this is an example of a product sheet, again, for other bituminous coal. And you can see that first on the left side, we have the time series of all the flows as it was table 1. Then we have calorific value. If you scroll down, here is on the top right side, but in reality in the worksheet is below that. You can see also from the numbers of the row. And then you have also imports by source and exports. Now the remarks page, that's very important for us because of course you are the people who know best about your country. So please give us some additional information here if there is something more complicated or something specific happening in your country. And here we can try to avoid some unnecessary query that we still do sometimes, but we do our best to reduce them. And very importantly, if you recall from the menu sheet, you have the check data button where you can select a year, or if you select no years, it will check for all the years. Now, this check data checks for consistencies and arithmetic check between tables of the questionnaire. So for example, you can see if the total of subflows is the same as is aggregated quantity, if imports and exports are different between tables, if there are negative values where there shouldn't be, or if calorific values are very different from the range that we expect them to be. Now, there can be a situation where these calorific values are different, of course, but still it's good to have them here so that we know that we can have a discussion and have more information from you about this. We said about consistency within questionnaires, which is very important. It's very important also consistencies with the other questionnaires, in particular electricity and heat questionnaire, where the inputs to power plants have to be the same as the one reported in the coal questionnaire. Let's have here a look. I will use again the laser pointer. So we see here that the same amount, which is reported in the coal questionnaire here on the left and the electricity questionnaire on the right, the amount of coal is the same. Then in the coal questionnaire, we also report the calorific value. We don't do that in the electricity questionnaire. We will see that later, but we report the fuel input in terajoule, from which you can back calculate the calorific value. Now, here we also in the electricity questionnaire, we report the gross electricity production, and from that we calculate the efficiency. We can see that here the calorific values are different between the one in coal, which is reported, and the one in electricity, which is calculated. So they will give different efficiencies. In this case, here it's the file where we see that, and it's our check file. In this case, we will have to query the country because there is no consistency between the two questionnaires. Finally, we have the reporting of coke ovens to show you that there has to be consistencies also within the tables of the questionnaire. So we have here reported the input, then the use in transformation in coke ovens, and we have also the report in table 1 of the outputs, coke oven coke, coal tar, and coke oven gas in the production line. Now, taking all these values, converting them to energy, putting this at the denominator, and this amount at the denominator, that's coking coal, we can calculate the efficiency and be sure that that's not over or distant from the range that we expect. So that's all for the coal questionnaire. But of course, if you want to have more information, because I couldn't go, of course, over everything about this questionnaire, but also other questionnaire, you can visit the IEA Statistics website, where you will find the questionnaire in Excel files and the reporting instruction for the questionnaires, but also the energy statistic manuals and the recommendation from IRES. Finally, a little bit of the things that we do in the energy data center of the IEA and of the data that we disseminate. Some are for purchase, but there is really a big ton of free products that we have here. The keyword energy statistics, which is a summary of our data, the data and statistic data browser, many more, the weather for energy tracker, which is a new platform with the weather related data related to the energy industry, and so on. And also our data feeds a lot of analysis from the agency, a lot of reports that you see on the right side. Thank you very much. That was all for my presentation. Now I leave the floors to you, and you can always send comments or questions to the email that you see below. Thanks.
We are going to discuss electricity and heat in our energy statistics, and with some first world key trends, current key trends on electricity statistics, and then key concepts on how we report and display electricity statistics in our methodology. And of course, at the end, we will answer some of the questions, so do not hesitate to ask them in the chat, and if my colleagues can reply, they will, and we will discuss on those at the end of the presentations. So let's move and discuss some of the key electricity trends in the world today. So let's start with the broad electricity production in the world. As you can see, between 1974, when the IEA was founded, and 2018, the amount of electricity produced, so in terawatt hours here, almost quadrupled and grew up to more than 26,000 terawatt hour. So this displays the evolution of the world and the development of many activities of the population and of the economies overall in the world. The only time in this time period when the electricity production decreased from one year to another was actually between 2008 and 2009, when the economic crisis hit the world. So now, if we focus a little bit more on what are the sources of electricity production from primary fuels, here you can see display pie chart on which fuel represent which sources of the electricity generations. So as mentioned previously when we discussed on coal, it still represents 38% of electricity generation in the world in 2018. So it's, as we discussed, it's far from going away anytime soon, and it still represents a big share of electricity generations. Overall, almost 2/3 of the electricity generation in the world comes from combustible fuel. This includes biofuel and waste, natural gas, oil, and coal. One thing to note here, but as you can see, wind and solar, so renewable sources, are growing really fast have been growing steadily and fast in the recent years, and they now represent more electricity generation than oil, for example. So those electricity sources are developing pretty fast. So now, if we start a discussion on where the electricity is more generated in the world, here is a time series of the electricity generations in the OECD countries and outside of the OECDs in red. So obviously you can see that this production in non-OECD countries grew far more quicker than in OECD countries in the last 20 years, roughly. And in 2011, it actually went non-OECD countries produced for 2008 actually produced more than OECD countries for the first time in terms of electricity. Now, this is still a little bit too general, so let's focus on which region outside of the OECD we are talking about. So obviously here you can see that these electricity generations grew the fastest in China and also in other non-OECD Asian countries. But this is on the most visible information. In all of the regions, the electricity generation grew a lot, almost quadrupled everywhere in the last 20 years. So that is a major development due to development of the economies, of industries in those countries, and also of the development of the increase of the level of life for the population there. And of course, if we focus now on which sectors in the whole world consume the electricity, we can see that obviously the industry remains the largest consuming sectors in the world. However, the residential and commercial sectors are increasing their share pretty fast due to the change in many economies from industry focused toward industry, toward residential and services focused. So we can see especially this in the next slide. One thing before we move on, as you can see, it quadrupled also, the consumption of electricity quadrupled since 1974. But if you pay attention to the level, we reached only around 20,000 terawatt hours, when in the production we reached 27 terawatt hours. So we are missing 5 terawatt hours. We will see later where those missing 5,000 terawatt hours are. But if you have an idea, don't hesitate to share it in the chat if you want to participate a little bit. So if we focus, as I was saying, on, let's say, a distinction between OECD and non-OECD, we can see here what I was saying, but depending on the economy structure of the structural structure of the country, you would have, of course, different share of the consumption by sectors. in OECD countries, we can see that residential and services represent a lot of the electricity consumptions, around 2/3, and only the last third for industries. When in non-OECD countries, the industry represents a big share, more than a half of the consumption of electricity. This, of course, depends and varies a lot when you are focusing on on the selected countries. Some countries in Africa do not have at all the same profile than China, for example, or Brazil, but it's still a general view that could show you, that could be a good indicator for you to compare the data. One last trend that is actually pretty recent, it's the impact of COVID-19 on electricity demand. So of course, in last year, the electricity demand and generation was deeply impacted by the world crisis. Globally, weather-corrected electricity demand decreased by around 2.5% in the early half of 2020. You can see it at, sorry. You can see it here with the first lockdown for some of the European countries. The decrease of electricity consumption reached almost 30% in some of the countries. For example, France here in green. And it was so between March and April, so during the hard lockdown in those countries. Since then, the demand increased again steadily until the period of October, November, where we had the second wave in those countries, and we can see again a decrease that is less important, but still a decrease here. In some countries, though, the demand already went above and the usual demand at that season for the electricity. So now we have seen some of the key trends. Now let's turn into some key concepts, unless there are some questions. I don't think I've seen one in the chat.
No questions so far in the chat, Nicola.
All right, let's move on then. Thanks, Ridan. So some key concepts. So we'll see per slide one key concept on how we report data and how it applies for our data collection systems. So first of all, let's look at the sources of electricity. Electricity can be produced as both primary and secondary energy, depending on what is the primary source of energy in your data. For example, here, primary electricity will be obtained from natural sources such as hydro, solar photovoltaic, wind, tidal or wave energy, for example. Secondary electricity is obtained from the heat generated by burning a combustible fuel such as natural gas, coal, etc., but also from the heat from nuclear fissions, geothermal heat, or solar thermal heat. So those are examples on distinctions we do regarding the electricity, primary or secondary. Same thing can be done for the heat. So primary heat would be actually the same as I just said, so solar thermal, geothermal, and nuclear fissions. And secondary heat will be obtained from the combustion of fuels, so fossil fuel or biofuels, and also from electric boiler or heat pumps. Another distinction we do now is on the type of producers. We can go at several levels here. The first one will be the distinction between main activity producers and auto producers. Main activity producer generate electricity and heat for third parties as their primary activities. For example, the main purpose of the facility is to generate electricity or heat, like a nuclear power plant or a hydro dam. And by contrast, auto producers generate electricity or heat only as secondary activities and as support of their primary activities. For instance, a large chemical manufacturing facility who may have on-site a power plant to generate electricity and or heat, and that will so sell part of its production more productions into the grid. Also, distinctions can be done between the plant that produce only electricity, so electricity only, heat only, and CHP, or combined and heat and power. So those generate both electricity and heat at the same time. This is also known sometimes in some literature as cogenerations. So on reporting convention for those different type of electricity or heat plants, we for main activity producers, so remember those that for whom it is the main source of revenue, the main objective of the plants or the structure, the convention is pretty simple. All productions of electricity or heat is reported. So we don't ask questions there. For auto producers, there are some specific conventions regarding heat. This is because auto producers are also industrial consumers that use fuel to power their processes. So for auto producer, all electricity produced is reported in the electricity and heat questionnaires, but also in other sources. That's what we recommend if we follow IRIS methodology. And for heat, we report only the heat sold in the heat-only plant. The amount of heat generated for own use on-site are not reported here. Similarly, when reported the associated fuel inputs to electricity and heat production, or to CHP, only the amount of fuel input associated with food sold are reported. So again, for CHP and heat, remember that you report only the heat sold by the plant toward the grid. So now another distinction that we can do is between gross and net production. I think we had a question yesterday that was regarding this subject and efficiency later on, so I will spend a little bit more time in here. So this gross production refers to the total output of electricity or heat generated in a facility before any of it is used. So this is the real first output of this power plant. However, not all of this is used for production, for productive purpose beyond the power plant. Some of the electricity and heat generated is used on site at the power plant for lighting, heating, and to support the plant operations. So all those consumptions, we define them as on use. The remainder between the gross production and on use is what we call the net production. This is the electricity or heat that is distributed toward the grid outside of the power plant. And remember that in the case of auto producers for heat and in CHP and or heat only plant, you only report the heat sold. So now let's focus a little bit more on the on use. So the reporting convention of the on use, such as the reporting convention of the productions. So for main activity producers and for all production of electricity, as previously, we report gross minus on use equal the net production. So this calculation here is pretty simple. It is the same for electricity only auto producers. However, for auto producers for heat only and CHP, we have specific rules. In the case of heat only, we assume that the gross is equal to the net, since as I told you, we only report the amount sold by the plant and not the rest. And same for CHP. So remember that in the case of reporting conventions, the only exceptions are for heat and CHP auto producers regarding heat sold. Now on supply and demand. In terms of supply, it is pretty simple. You have the fuel input toward the power plant or the production from natural sources. So fuel input of natural gas, coal, or biofuels, heat generated from nuclear plants, and you obtain the gross production, as we said before. The unused is subtracted to it, with the exception that we know, to obtain the net productions. After, when we have this net production in our data sets, now we need to see some specific consumption that can be done in storage hydro, pump storage hydro, electric boiler, or heat pumps that are specific elements. I will not spend too much time on it there. Then you can have some of the electricity that is in trade, so import or export with other countries. We will see at the end of the presentation a specific slide on this. And in the distribution, you can have some losses, but we will discuss in a few slides on it also. And once you subtracted all of those elements, you get the final consumptions on residential, industries, services, etc. So in theory, the difference between the supply and final consumption figures should just be losses and the rest of the elements that we see there. Of course, there may also be some statistical differences due to the differences between when you create the data in the power plant and in the final consumption sector, for example, there might be some differences. Also, one last element, we try to collect, and many international organizations try to do so too. We try to collect now the peak load and capacity data, which can be very useful for electricity analysts around the world. So if you can collect those data, it can be very useful. Now, let's focus a little bit more on the transmission and distribution losses. So in the previous slide, we saw that losses are the main differences between supply and consumption figures. So just to give you a little bit more detail on the magnitude of the losses you should expect in your data. As electricity travels through the cable and transformers, energy is lost along the way. Much of it is form of heat in the cable. And as the electricity current flowing through the cables raises its temperatures, it produces heat within the cable, and this is, of course, lost. And in general, losses should be expected around 5 to 15%, depending on the states of the distribution network and if there are or not thefts going on the electricity distribution system. Higher, so if you have some old set in some of the distribution networks, you have some old parts badly maintained, you should expect there more losses between the net production and the consumptions in your end users. So globally, transmission and distribution losses represent around 8% of total gross productions. And energy industry unused represent also about 8% too. So in total, around 17% of total gross production, a sizable amount is lost or used outside of the final consumption sectors. So here you can see, as I told you a little bit before, the difference between the roughly 27,000 terawatt-hours of electricity productions in the world and the final consumptions of only 22,000 terawatt-hours. So with the 16% missing that are actually the unused and losses. So regarding the generation's efficiency, now if we have a look at another important concept and something that we check a lot when we receive data and we work on them, it is the efficiency of the transformations. So it is calculated as the total gross energy produced, and I insist on the gross, so you take into account the unused that will be subtracted later on for the net to obtain the net productions. And you divide these figures by the energy content of the fuel used as input. So it is energy out divided by energy in. And I insist also on the energy. When you calculate the efficiency of the transformations, especially for heat or electricity generations, you should use energy units to be sure that you have the correct elements. According to the first law of thermodynamics, you cannot create or destroy energy, so the efficiency must be less than 100%. You cannot create energy out of nothing. So the expected efficiency will vary depending on the fuel, of the technology, of the maintenance of the power plant. So of course, the latest natural gas power plant, for example, are far more efficient than some 30, 40-year-old coal plants that were not maintained properly in the last decades. So, any guess? No. Sorry, one moment, a little bit there. Sorry about this. So here is an example in the graph below. So let's say you have 100 units of fossil fuel as input into a power plant. The output will be 45 units of heat and 20 units of electricity. So this is a CHP plant. And when you calculate the efficiency, you just calculate the output here divided by the input. So 65%, which is a high efficiency, which can be found in latest CHP cogeneration plants. The difference being the heat lost during the transformation that cannot be captured or used by the plant. So moving on, now we'll see the reporting conventions for trade of electricity. So unlike other fuel, trades of electricity and heat is reported on the basis of border crossed, not on the origin of the destinations. This is because electricity, of course, is not exactly a fuel. It is a flow of electrons through the cable. So it is harder to just focus on the origin of destination. Sorry, there are some noises outside of my place. So let's see an example here. Let's say if Portugal was to export electricity to France through Spain, then as France and Portugal do not share a common border, they would not report trade with each other. And it would be actually with Spain. So Portugal would report exportations towards Spain. Spain would report imports from Portugal and export towards France. And finally, France would report imports from Spain. So Portugal and France will not report trade with each other. The difference from the convention used for other fossil fuel or biofuels. Some small reminders on some physics and elements. The distinction between energy and power when we talk about the data. Simply put, power is the rate at which energy is used. So power is simply energy divided by time. Power is measured in watts. So energy is measured in joules. So 1 watt is equal to 1 joule per second. So if 1 watt of power used in 1 joule of energy in 1 second is if we have 1 watt of power used by 1 joules in 1 second, in 1 minute you would obtain 60 joules, and in 1 hour you would obtain 3,600 joules. This, as you just witnessed, can be pretty tiresome to say and think on. So to ease and for convenience, we called 3,600 joules a watt hours. So this is the energy that you are more used to now, watt hour. And this is the amount of energy that 1 watt of power would use in 1 hour. it is an important distinction what's referring to power and what hour referring to energy. This concept will be useful for the next topic that we'll see just right now, which is capacity. In addition to production, consumption, trade, we try also to capture data on power plant capacity, specifically on net maximum capacity. Net maximum capacity is simply the maximum power output that a power plant can produce with all plants running at full blast, and by conventions, we say on the 31st of December of the reporting year. So these data are very useful for analysts to have. However, they can also be useful for statisticians when checking the data, as we can compare actual reported productions values with the maximum potential productions values to check if the data made sense. This value, actual productions divided by potential productions, is called the capacity factor. Again, it should be less than 100%, except if there were plant closure near the end of the year, in which case the figure might be distorted, of course. And there are different expected values depending on the technologies. For instance, nuclear plants are expensive to build and therefore are typically run as much as possible, whereas solar PV, which does not run at night and is both weather and location dependent, will have a lower capacity factor. So as statistician, we can use both historical and expected capacity factors to check our data, and analysts will also do the same for their models. So finally, some comment on data collections and sources of data before we move on for the next presentations. As with all statistics, data collections has cost in terms of time and money, but also in terms of opportunity cost. Therefore, a balance must be struck between available resources and needs. This said, it should be kept in mind that not having a proper information available for informed decision making can lead to higher costs. So an argument when you are explaining your needs in terms of budgets. In terms of specific challenges for electricity statistics, we have the liberalizations of electricity markets is having an impact. Previously, there were monopolies. All the electricity data could be gathered from just one company in the country, and now data needs to be gathered from many different companies, some still big ones and some smaller ones. In addition, competition leads companies to be reluctant to provide data, and also this leads to confidentiality issues. So this can impact data coverage and comprehensiveness. And then, similar to other fuel, resources limitation in statistical office and high staff turnover can cause data quality to suffer. Finally, in terms of data collections, the objective of the collection system is to have detailed and reliable data on the different parts of the production and consumption chain. And for it, we need a mature and sustained energy statistics system. To facilitate all this, there are a lot of elements that I think we already discussed before in other presentations. You can establish legal basis, establish proper reporting mechanisms in the form of questionnaires, network of contacts, agreed timetable with the various stakeholders. You can also establish proper dissemination mechanism, which can enhance the importance of your data collection for the stakeholders, and allocate proper resources to collect, process the data, review method, and at the end of your data cycles, of course, it's important to review your methodology and process to anticipate and adapt to changes in the energy situations in the futures. So what are the type of data collection for electricity and heat information? So you have surveys that are the big elements. So surveys toward power producers, transmission and distribution system operators, enterprise, household, etc. But not only this, you can also have administrative data that comes from energy regulators, the customer office regarding the trades, and data created from program and policy implementation, for example, when checking energy efficiency policies effects. Something that has been developing in the recent years are the smart meters that can complete the conventional meters to do some direct measurements of the electricity consumption, for example, in residential sectors. And finally, when you are missing data, you can always use estimation and modeling using, as we said before, for example, plant capacity informations, if you are missing the data, the energy productions, to complete your data set if you are lacking something. With this, we reach the end of this presentation.
Thank you very much, Nicola, for that presentation on electricity. And again, if anyone does have a question that wasn't covered here, please don't hesitate to contact us through the email addresses. So now I'll hand over to Taylor. We'll move on to the last of the two presentations today, and Taylor will talk us through renewable statistics.
Thank you very much, Aidan, for the introduction. I will share my screen. Okay, thank you very much. So today I will be presenting the Renewables and Waste Annual Questionnaire Overview. And as Aidan mentioned, my name is Taylor. So first I will be discussing key renewable trends in order to give you a perspective of where renewables are positioned within the total energy supply. Next, I'll move on to key concepts, including classifications of renewables, as well as special issues we encounter when reporting liquid biofuels. I'll also discuss briefly data reporting and checking, collection, and use. And finally, I will discuss key points for renewable data reporting, specifically as they pertain to the renewables questionnaire. So I'd like to start by posing a question to you. So which renewable energy source do you think takes the largest portion of electricity production in the world? So as you saw before, I have a Menti available to take your answers. So we have not used this in this session, I believe. So for those of you who are not familiar, you can go to www.menti.com and use the code at this top of the screen in order to submit your answer. So I'll give you a couple seconds to go to the site and tell me what you think the correct answer is. I can see in the chat that it's not the same question. So I think perhaps in the interest of time, we'll skip the Menti for now. Sorry about that. So the answer to this question was in fact hydro. And a key thing to consider in this question is that we're asking about electricity production, because as you will see later on in the presentation, this answer will change when we're looking at the total energy supply. So continuing to examine electricity production, we can see that renewables is the second largest source of electricity production in the world as of 2018. At approximately 25% of this electricity production. And indeed, hydro is the largest contributor to this. And a reason for this is that hydro is a very established technology that can produce a large amount of electricity because of the large capacities it has. But we can also see that solar, wind, and geothermal, which is presented as an aggregate here, as well as biofuels and waste contribute as well. Another thing to note within this figure is that renewables and natural gas, which is the third largest contributor, are very similar in size or in share. And this actually can change from year to year depending on conditions, as hydro is highly dependent on weather conditions such as rainfall. So while this is not very likely to change on a global scale, this is far more impactful to the electricity production shares at a regional level. So now looking at total energy supply, we can see that renewables has a much smaller share. We can also see that now, instead of hydro being the top contributor among renewables, we have solid biofuels being the largest. And this is because solid biofuels plays an important role in heating and cooking, which is not, of course, included in the electricity production figures. This slide examines average annual growth rate of renewable supply from 1990 to 2018, so approximately last 30 years. And we see right away that solar PV has the largest growth rate at approximately 36%, followed by wind. And a reason for this is that these are fairly new technologies, and particularly for solar PV, we've seen the price of solar photovoltaic panels drop significantly in the last couple of years. And so this is causing the market share to increase. Another influencing factor is the sustainable energy policies that have been put in place by many governments around the world that is promoting the growth of these technologies. On the other end of the spectrum, we can see that hydro and solid biofuels are the smallest growing renewables. For hydro, it's just slightly larger than the total energy supply growth rate. And this is partially because it's an established technology that has already experienced a lot of its growth, but also because it's constrained by geography and access to a good water source that solar PV and wind do not have the same constraints. Finally, for solid biofuels, we can see that this is actually the only renewable that is growing slower than the total energy supply growth rate. And it's contributing factor to this is that solid biofuels do not, while renewable, they don't actually burn cleanly. So therefore, they're not ideal for residential use because of health factors as well as carbon emissions. So there's been motivation to move away from the use of solid biofuels towards cleaner burning fuels. Now we'll look at share of renewables by region and by sector. So first, looking at region, we can see that Africa has the largest share of renewables in their total energy supply at nearly 50%, followed by non-OECD Americas. And the reason for this is that solid biofuels, as I previously mentioned, are a large component of the renewable supply. These play a very important role in developing countries. Now looking at the graph on the right of consumption by sector, to support this, we can see that residential, which is where solid biofuels are commonly used for cooking and heating, has the largest sectoral consumption. Here is presented as an aggregate of residential, commercial, and public services. This is followed by electricity plants, which is where hydro comes into play. And then the third largest share is industry. Currently, industry sits at only 10%, but we expect this to grow in the coming years as large corporations and governments look towards cleaner, renewable energy sources for their industrial activities to decrease their carbon emissions and meet their climate goals. So now moving on to the second portion of the presentation, which will look at how renewables and waste are reported in energy statistics. We have these 4 categories that renewables are divided into. The first category is non-combustible electricity only. And in this category, we have hydro, wind, solar, photovoltaic, tide, wave, and ocean. And these fuels are in this category because electricity is the first useful energy form that we have available from these sources. So we do not look, for instance, at the mechanical energy of hydro. The second category is non-combustible heat, primary, and electricity secondary. Nicolas talked about this in the electricity questionnaire presentation, but as a reminder, geothermal and solar thermal both are extracted as heat as primary energy. In the next category, we have combustible fuels with stock changes. So these fuels are both combustible and storable, as the category name implies. So in this category, we have solid biofuels, waste, liquid biofuels, and biogases. And in the fourth and final category, we have heat pumps. So heat pumps use ambient air to extract heat, but this is not as common, so we will not be discussing this category in detail in this presentation. So I would first like to go into depth of looking at solid biofuels. So solid biofuels covers organic, non-fossil material of biological origin, which may be used as fuel for heat production or electricity generation. We distinguish primary and secondary solid biofuels, secondary solid biofuels being defined as being manufactured through a transformation process. So most of the fuels that we look at in the renewable questionnaire are indeed primary solid biofuels. The primary exception to this is charcoal, which is a secondary product, which is produced from the pyrolysis of wood products. So as you can see, there's a wide variety of different primary solid biofuels that are reported in the renewable questionnaire. I would like to draw your attention to just two at the moment. So the first is black liquor, which is a byproduct of paper production. Despite the fact that it is a liquid-like substance, it is reported in solid biofuels by convention. The second product I would like to bring your attention to is industrial waste, the renewable part. So we do consider the renewable part of industrial waste to be a solid biofuel. However, the non-renewable part is not reported under solid biofuels and has its own category. So therefore, it is important to separate these two components when filling in these energy statistics. And this separation can be done either with knowledge of the composition of the industrial waste or using estimation. So now I would like to ask you, what is an example of how wood is used in energy statistics? So I'll give you a couple seconds to think about what the correct answer is. Okay, so the correct answer is number 2, burning for home heating. So I'll briefly explain why the other two answers are not correct. So the first option, as material for making furniture, because wood is not being used as an energy source here, it's used as a material for furniture. We do not consider this within energy statistics. And in the third option, wood residues burned in a landfill, because we assume that the energy produced is not captured and is instead just allowed to disperse. We do not count this in energy statistics. However, if the energy here was being captured and used, then it would be considered. Moving on from solid biofuels to liquid biofuels, I would like to discuss how these are reported in the renewable and oil questionnaire. Because liquid biofuels, particularly, or they mainly consist of bioethanol and biodiesel, are often blended with similar oil products to create a blended final product. It's a bit tricky when we look at how to report them. So the main thing to consider is that when reporting liquid biofuels within the renewable questionnaire, we ask that you report only pure biofuels. So in this case, trade and final consumption between the renewable and oil questionnaires are not comparable, because the trade reported in renewables will be of only pure biofuels, where the trade reported in oil are exclusively blended products, and of course, normal oil products. So to better describe this methodology, I have an example here. So a country produces 1,000 kilotons of diesel containing 10% biodiesel. Half of the diesel is exported and the other half is used in road transport. So I'll give you a second to consider how much would be used in the renewable questionnaires, or reported in the renewable questionnaire. The answer would be 100 kilotons of biodiesel production should be reported in the renewable questionnaire, because this is the pure amount before blending. And then, because the exports and final consumption is of blended products. These are then reported in the oil questionnaire, and no exports or final consumption would be reported in this scenario in the renewable questionnaire. So there is one thing to consider that is similar between the renewable and oil questionnaire, and this is in the renewable questionnaire, the transformation, under transformation flows, it's for blending with motor gasoline, diesel, and kerosene. So this is where you would put the amount that is being transferred and blended to oil products. And then consequently in the oil questionnaire, this relates to receipts from other sources. And it is important to maintain consistency between these two flows. So finally, it's important to note that while many of these products are blended, some countries do have consumption in road transport for pure biofuels, which is reported in the renewal questionnaire. And this sector is expected to grow in the coming years as consumers look for fossil fuel alternatives. This is also similar for electricity and heat production, which can also be reported in the renewable questionnaire for pure biofuels. Now I'd like to discuss different data collection methods and data sources. So I will go through this briefly as my colleagues have already touched upon this today. So for renewables, we have supply data that comes from surveys and administration data. We also have demand data that comes from end-use surveys from households and enterprises. However, we also recommend an integrated approach that uses both supply and demand data, as well as estimation and modeling to create a more complete picture of the energy flows. So looking more closely at data collection, we have surveys is a very important data collection method for the renewable questionnaire because of solid biofuels. Solid biofuels come from many different sources and have many different points of consumption. So surveys can be a very powerful tool for getting this information. Administrative data is also important to consider for renewables, as many renewables such as solar and wind are growing as a consequence of policies being applied. Therefore, administrations are often tracking this data. And then finally, we have direct measurements and estimation and modeling, which my colleagues have already discussed. So now looking at who uses this data. Well, there's many institutions outside the IEA that can use energy data for a variety of purposes. Some of these purposes include in assessing security of supply. Pardon?
I think you can go ahead. I'll ask you muted.
Oh, sorry. Okay. So as I was saying, assessing security of supply. This is important for building plans for a resiliency within an energy supply. We can also use this to compare countries to track progress and benchmark, as well as measure environmental policies and policies. So for instance, to see how a country is progressing towards its climate change goals, as well as informing policy and business decisions. So you've already seen this slide before, but as a reminder, we have a lot of resources available to you involving energy statistics, including renewables. So now I will briefly go over the structure of the renewable questionnaire. So I would like to point out that even if your country is not currently reporting using the renewable questionnaire, I hope that this section is still useful to you because as it informs of the IEA methodology, the methodology that we're using, and I hope can be used as a guide as you look to improve your energy statistics. So in table 1 of the renewable questionnaire, we have this divided into electricity and heat and main activity producers and auto producers. Nicolas has already described the difference between the two of these. I would just like to emphasize that only report heat sold to third parties for auto producers. I would also like to point out that for the renewable questionnaire, we are only looking at gross electricity and heat production. So net electricity and heat is reported in the electricity questionnaire. Also, another point on this, this table corresponds to table 1 in the electricity questionnaire. So it is important to maintain consistency between these two tables across questionnaires. So in table 2A, we have across this top row 13 energy products as defined by the International Recommendation for Energy Statistics. And you will recognize these products as the first categories 2 and 3 of renewables that I presented earlier. So these are combustible fuels, geothermal, and solar thermal. And then along the column here, we have 60 flows as defined by the International Standard Industrial Division. So these are divided into supply, transformation sector, energy sector, and final energy consumption. And within final energy consumption, we have the industry sector, transport sector, and as well as other sectors, which includes residential. So it's important to note that in the transformation sector, here is where we report input to electricity and heat plants. And if you report output in table 1 from electricity and heat plants in either gigawatt hours or terajoules, then in this table, we should have the corresponding input that created that output. And the efficiency can be checked, should be checked either manually using the method that Nicolas described, or in the renewable questionnaire, we also have sheets that automatically calculate this efficiency for you. So it is important to make sure that these efficiencies are within a reasonable range. Would also like to draw your attention to the units used for reporting. So most fuels we report in terajoules using on a net calorific value basis. However, liquid biofuels and charcoal are reported in kilotons. Now looking at table 3A, this is a table in which capacities are reported in the renewable questionnaire. So the first 23 rows, we asked for electrical capacity in megawatts. This is followed by solar collector surface in 1,000 meters squared. This is only for solar thermal collectors. Solar photovoltaic collectors are reported in megawatts. We also have the liquid biofuel plant capacity reported in kilotons per year. And this is concerning the production of these liquid biofuels. Finally, we have average net calorific values. We ask that these are reported for liquid biofuels and charcoal. And it is important that the net calorific values reported for the liquid biofuels match those reported for liquid biofuels in the oil questionnaire. Next, we have table 4. So this is where we ask you to report solid biofuels production in more detail. So in the different types of solid biofuels I described earlier, as well as biogases in their subcategories. What is important to note here is that the total solid biofuels reported in table 4 should match the total solid biofuels reported in table 2. Finally, we have tables 5 and 6. These are actually separate tables, but we have combined it in this slide for easy viewing. So we have these tables to report trade for liquid biofuels in wood pellets. These are reported in kilotons. So it's a little tricky here because wood pellets in table 4 are reported in terajoules, but here they're reported in kilotons. So there is unit conversion there. And the totals at the bottom, total imports and total exports, should match the total imports and total exports for each fuel reported in table 2. Now, for my final slide, I would like to give you an overall perspective of how the renewable questionnaire fits in with other questionnaires. So there is a lot of overlap with the electricity questionnaire. So table 1 and table 3A from the renewable questionnaire should be consistent with tables 1 and table, I believe it's 7 on the electricity questionnaire. As well as I already mentioned, there should be some similarities between the liquid biofuels reported in the oil questionnaire and the renewable questionnaire in specific flows. So unfortunately, we don't have a tool that allows for easily checking with it, between these questionnaires. So we ask that you manually check it and to try to maintain a consistency. And as Nicola mentioned in the coal presentation, for internal consistency, we do have tools within the spreadsheet that will allow you to check to make sure that internally all the math adds up and flows are reported and make sense. So finally, I have some helpful links here for you that you can refer to later. And I would like to thank you for your time and open up the floor to questions.
Hi, my name is Victor, and I work in the Energy Efficiency Indicators team together with my colleague Thomas and our manager Mafalda. And our main task is to collect end-use data from IEA member countries as well as non-member countries and to develop related energy efficiency indicators. This session will last around 50 minutes and we will use the Menti app. So please have it handy during the session. In fact, you can already start opening. And also at the end of the week, for those that you have enrolled, we will have a dedicated session for the exercises discussion, where we hope also to reinforce some of the concepts we are going to explain in this session. So that being clarified, in this presentation, we are going to cover why it's important to develop energy efficiency indicators, which information we can already find in the energy balances, which additional data to this one is needed for efficiency indicators, and how can we collect this data. And first of all, I would like you to start with a Menti question to remember what it is energy efficiency. For this, please switch to menti.com with the code 72496849 that my colleagues are going to put in the chat as well. And here, what I would like you to answer is if you agree or disagree with those statements, in the sense that if you think that those statements represent energy efficiency or not. So you have several options, 5 levels for each statement, and you have to say if you strongly disagree or if you strongly agree. So for the first one, do you consider energy efficiency to consume less energy to provide the same service? So for example, using LED bulbs instead of incandescent bulb to consume less energy and provide the same light? Or do you agree that it's energy efficiency to consume the same energy to provide more service? Like, for example, produce twice the amount of steel using the same energy? And what about consuming less energy because of a change in service? So imagine your economy is an industry-based economy and it switches to service-based economy. Which is less energy intensive, and therefore you will consume less energy to provide the same unit of GDP. Would that be energy efficiency? Do you agree with that statement? And finally, would that consume less energy and provide less service? Like, for example, instead of taking the car, walking or biking to our destination, or instead of taking the elevator, to take the stairs to reach our floor. Would that be energy efficiency? I'll leave you some time to answer. I see some consensus already, particularly for the first two. A little bit of more time. Okay, so yes, I actually agree with the two first statements, and actually this is what we are trying to do, right? That's what energy efficiency is. We try to do the same, consuming less energy, or at least do more consuming the same energy. So I would agree with the two statements, the two first statements to be energy efficiency. What about the third one? It's true that if an economy switches, for example, their structure to a more service-based economy, they are going to consume less energy and they are going to produce the same output or even more, consuming the same energy. However, this doesn't mean the economy is more efficient. They are just doing a different thing. So it's because of a structural change. It's not because the economy is being more efficient. And that's why I wouldn't agree that this is energy efficiency. And about the fourth statement, it's true that you can save energy, for example, if you walk instead of going by car to your workplace. However, the service is not the same. It's not as comfortable as taking the elevator as taking the stairs to reach your floor, right? So it's not energy efficiency. You're just doing something different. So you are conserving energy, but it's not energy efficiency. So now that we have more clear what is energy efficiency, let's continue. And let's see why it's important to develop energy efficiency indicators.
Sorry, is it possible to ask a question before you move forward, or
sure?
Just regarding your example on walking versus taking the car, for example, I just want to understand how you what is the service? Is it per kilometers traveled, or is it kilometers traveled at a certain speed? So how do you compare, for example, a car and a train? Which one is more efficient? Yeah.
Okay, so for these units, how to measure, let's say, transport, we are going to cover it later on in the presentation. But the point really on that exercise is to exemplify that energy conservation is not the same as energy efficiency. So you can, if the distance is short, you can walk to your destination instead of taking the car, and then you are not consuming energy. But this doesn't mean it's more efficient, because it's totally different things. The speed you go by car, the comfort you have in your car is not the same as walking, or even the distance you can reach with the car. But of course, when we are comparing different vehicles, we have some units that we'll see later on in the presentation. And yes, we measure it with passenger kilometers, for example.
Okay, thanks.
No problem. So usually when we think about energy efficiency and why it's necessary, we all think about the reduction in energy consumption. However, there are many other benefits from energy efficiency. Here we can see what we call the energy efficiency flower, representing multiple benefits from the energy efficiency improvement. And those benefits can be economic, social, environmental. For example, energy efficiency improvements can increase employment, can increase energy security, or it can even reduce harmful emissions like CO2. And this is why many countries have set energy efficiency targets, and this is why it's so important to have end-use data to track the progress of energy efficiency policies and to be able to set the correct targets for these policies. Here we can see some examples of policy designs and also benchmarking exercises. And lately we had a lot of requests for end-use data and efficiency indicators for those benchmarking exercises where you, for example, compare internationally a sector with other countries. So here, for example, we have the Atlas of Energy Efficiency from Brazil, that it contains a chapter that it's a benchmarking chapter for the industry sector. However, it's estimated that only 35% of the global energy use is under mandatory policies and regulations. So this means that there is still a huge potential for applying efficiency policies and regulations. This is why it's very important to have detailed data in order to be able to study energy efficiency trends, to know the priority areas, and to set the targets and to track and monitor the actions in place. But now let's see which information we can find already in the energy balance. With the data that we find in the energy balances, combined with some macroeconomic data, we can already define some high-level indicators, like the energy intensity or the self-sufficiency. We can also find the shares of final energy consumption, such as the total residential consumption, total industry consumption, total transport consumption. We can even find some subsectoral detail in the industry sector, like the chemical and petrochemical consumption or the iron and steel consumption. So there is a lot of valuable information already in balances. And these data are already very useful to identify which sector in our country could be a priority to apply energy efficiency measures and try to reduce the energy consumption. So here, for example, we can see the shares of the United States total final consumption. And the first thing that stands out is that we can identify that the road transport is the most consuming. So it's likely that we consider the road transport a priority sector for energy savings and to apply measures and regulations. However, we need more detailed data to better assess this, because, okay, we know that all this consumption is coming from the road transport, but we don't know if it's coming from cars, if it's coming from trucks, if it's coming from the aviation. So we need more detailed data, for example, consumption by vehicle, cars, buses, trucks, or and also activity data, like the distance traveled by all those vehicles, passenger and ton kilometers. So as your colleague was asking, we need all those kind of data, not only consumption data, but also activity data, to be able to compare between one type of transportation and the other, and to target the policies to the correct sectors or the correct vehicles in this case. Also, energy intensity is commonly used as a proxy for energy efficiency. However, the indicator is too high level and includes other factors apart from energy efficiency, such as the structure that we saw, the structure of the economy that we saw in the first question, in the third statement, or the activity. So the increase in population, there are more cars, more houses, more equipment. So, for example, a country can reduce the amount of energy needed per unit of GDP, which is the energy intensity, but this doesn't mean that the country is being more efficient. Because this decrease could be just what we were mentioning before, that the country is switching from an industry-based economy to a service-based economy that is less energy intensive. But this doesn't mean, again, that it's more efficient. So if we want to study energy efficiency, we need more detailed data. So in here, what we can see are different residential indicators. And the first one, the first blue line, represents the total residential energy consumption. And we can see that at the end of the period, this has increased 15%. However, if we have a look at the red one, the next one, it corresponds to the total residential consumption per capita. And we can see that this has decreased at the end of the period compared with the year of reference. And if we look at the total residential per dwelling, the green line, we see that this has decreased even more than compared to the red one. But we can go even further and correct this time series to avoid the effects of climate. So the purple line is the same as the green one, but climate corrected. So this means that we have omitted all the effects from the climate. So for example, if there is a cold winter, naturally people will consume more energy for space heating. So it's likely that the residential energy consumption will be higher for that winter. So for example, we can highlight in 2009, you can see this peak in the green time series that it's not reflected in the purple line. And this is because it has been climate corrected. But we can use even more detailed data. So we can use the residential space heating energy consumption temperature corrected per dwelling instead of total residential consumption. And we can observe that this has decreased even more than the other indicators. And we can go even further, and instead of per dwelling, have an indicator of residential space heating temperature corrected per floor area. And we see that at the end of the period, compared with the year of reference, this has decreased 35%. So we cannot say only by looking at the total residential consumption that we are less efficient now because we are consuming 15% more energy. This is probably because of an increase in activity. There are more people, there are more houses, there are more appliances, more mobile phones, more computers. But if we pay more attention to the detailed data, we will see that in fact now we are more efficient for space heating. We are using 35% less energy to heat the same surface as the year of reference. So the message here is that we really need to choose the indicators that are appropriate for the message we want to give. So if we want to implement a policy to improve space heating efficiency, we will need more detailed data. It won't be enough with the total residential consumption or the total residential per capita. We need more detailed data. Otherwise, we have the risk of applying a policy that is not well targeted or directly a wrong policy. So what drives energy intensity then? The efficiency progress, of course, is one of the drivers. For example, more efficient industrial processes will contribute to a lower overall intensity. But there are also other factors like the increase of activity, as we were mentioning, more people, more houses, more cars, bigger houses, and all this will push the energy consumption upwards. And also the structure of the economy. As we were commenting, if the country switches from industry-based to a service-based economy, the energy intensity will be lower. So here we can see, for example, that the yellow line is the energy consumption, and we see the effect of the energy efficiency, which corresponds to the green line on the bottom. We see that this pushes backwards the energy consumption, but the activity on top, the blue on top, it's increasing the energy consumption, in fact. And the structure, it's also decreasing a little bit this energy consumption. So it's really important to disentangle the efficiency effect from other effects to be able to know if our policies, of our efficiency policies, are actually working. Because if not, it's impossible to see if this decrease is being because of a structural change, if it's because the activity is lower now. So having the detailed data to be able to do this is essential. But which additional data are needed in order to study energy efficiency then? As we have seen from the energy balances information, we can already create some energy indicators such as the total final consumption per population. However, those indicators are not specific enough to monitor energy efficiency. In order to study energy efficiency and obtain energy efficiency indicators, we need end-use data or even more disaggregated data. Like, for example, the space heating per square meter that we saw in the time series example. However, the greater the disaggregation, the more data are needed, and usually this also comes with a higher cost. It's true that collecting data is costly, but with more detailed data, we can better design the policies. So not having the proper data could lead to incorrect decisions and actions, and as a consequence, to even higher costs. Also, in order to develop indicators, apart from energy consumption data, it's essential to also collect activity data. So the activity data usually are sector specific, and it could be, for example, the physical production of a certain commodity like cement or steel, or floor area or distance driven by a vehicle. And combining energy consumption and activity data, we can obtain efficiency indicators. And those efficiency indicators can explain how much energy is needed to provide a certain service. For instance, how much energy is needed to produce a ton of steel. And now let's have a look at what we collect at the IEA for this purpose. Of course, this is the IEA approach, and each country can have a different approach depending on the specific needs or the priorities. But we still think that this framework could be useful as a reference or guidance. So let's start with the residential sector. So for the residential sector, for energy consumption, we collect data by end use. This is by, for example, space heating, space cooling, water heating, cooking, lighting, and also by appliance, like the consumption from refrigerators, the consumption from the clothes washers. And also it's important to collect heating degree days and cooling degree days. This is very useful to actually make the climate corrections that we were mentioning before in the time series example. And with this, we can avoid the noise created by the effects of the climate. And if usually these data are available from administrative sources in your country, but if not, or if you like to compare or just to have a look, we just release the weather energy tracker that is for free, and you can consult it in the IEA. I'm sure my colleagues are going to put a link in the chat very soon. And regarding the activity data, we also collect population, number of occupied dwellings, residential floor area, and appliances stock and diffusion. This is, for example, the number of fridges and how many fridges per home there are. So now, please, I would ask you to go to menti.com for the last time. And in this occasion, what I'm going to ask you is we have several end uses in the middle, like for example, space heating, space cooling, water heating, lighting, residential appliances. And I would like you to link this either with occupied dwellings or floor area. So to link the energy consumption with the activity data you think it's more appropriate to create an energy indicator. So again, in this case, you have three options for each end use. You can either say, for example, space heating divided by occupied dwelling, or space heating divided by floor area, or in the middle, if you think that both could be a good option and there is not a strong preference for one activity data over the other. So now I'll give you some time to answer to this. I see in the chat a question about heating degree days and cooling degree days. I'll be happy to address that at the end of the presentation. And in fact, we have some complementary material to give you more detail about that. Okay, anyone else? We had 20-something responses for the last exercise. Any last response? It's the last Menti of the day. Don't worry, there are no more. Okay, so I start seeing some consensus. And yes, in fact, for the first one, space heating and space cooling, I agree with most of you in the sense that probably, well, first, let me say that, of course, this is an open question. Using one activity data or the other for our indicator will depend on what it is, what we want to reflect, and which are our needs or our specific conditions, or also which data are available, because maybe we don't have floor area. So in that case, probably occupied dwellings will be the only alternative we have. But in the case of space heating or space cooling, it's true that it will probably be more accurate to account this by floor area. Why? Because it's not the same to heat or to cool a house of 20 square meters compared to one of 100 square meters. So therefore, it's more accurate, or it's better to use space heating or space cooling per floor area. However, in the case of water heating, if you live in a house of 50 square meters, you will probably spend a very similar amount of water heating compared to a house of 100 square meters. So it's more related with the number of people that lives in that dwelling. So probably occupied dwellings is already a good activity data to couple with this energy consumption. In the case of lighting, it's true that both activity data, both occupied dwellings and floor area, could be a good activity data for the indicator, because it's not a direct relationship between a house being bigger and using more lighting, at least not in a small scale, let's say. So in this case, it will really depend on the data availability and what's the message we would like to provide. And for residential appliances, in fact, the best option would be to couple this energy consumption with appliances stock. So for example, the number of fridges or the number of washing machines that we have in that country. So you have really the energy consumption per unit of appliance. However, if this data is really detailed and probably it's not always available, and in that case, probably a good alternative is occupied dwellings, since if you have a house, again, of 50 square meters, probably you'll have the same amount of fridges or washing machines that a house with 100 square meters, at least, of course, with some exceptions, but in general terms, you will have a good approximation with occupied dwellings. Okay. Let's continue then. And what I would like to reinforce about the activity data as well is that we should also pay attention to the activity data we use for our indicators. So for example, if we use total dwellings, we will also account for unoccupied dwellings and secondary residences. Therefore, in order to avoid counting in efficiency empty buildings which do not consume, we should exclude vacation homes and occupied dwellings. So the message here is that we should have the same boundaries for energy consumption as we have for the activity data. So if only the primary residences are mostly consuming the energy, it's better to consider only the occupied dwellings, the primary residences, as a denominator for our indicators, as activity data. Otherwise, the the accuracy of that indicator would be biased by all those unoccupied and vacation homes. Let's move now to the service sector, where we collect energy consumption data also by end use, similarly to the residential sector, space heating, space cooling, lighting. We also collect non-building use, like for example, the street lighting consumption, but also we collect service energy consumption data by IC category. So for example, the warehousing, the accommodation, and this is something we recently started doing since we realized that most countries had difficulties to collect data by end use, but it was easier for them because of how the surveys were designed, for example, to collect data by IC categories. And both data collections are very useful for the service sector. And regarding activity data for the service sector, we collect value added, service floor area, and number of employees. For the industry sector, we collect energy consumption data for the major IC subsectors, like the chemical sector, iron steel sector, but we also collect data for the most intensive industries, like for example, the aluminum production, cement production, clinker production. And we also collect activity data for value added and physical production. That the physical production corresponds to the production of those most energy intensive industries. Like for example, we collect aluminum production, we collect steel production. So we are able to produce indicators like, for example, the energy that we consume to produce 1 ton of steel. And finally, for the transport sector, we collect energy consumption data by segment. So this means passenger transport and freight transport, but also by mode. So passenger road, so for example, road, rail, air, water, but also the combinations. So you will have passenger road, freight road, passenger rail, freight rail, all these for energy consumption. And for the activity data related to the question you were doing before at the beginning of the presentation, we collect activity data for vehicle stocks, vehicle kilometers, passenger kilometers, and ton kilometers. And this, coupled with the energy consumption, we are able to do indicators that help us making the comparisons you were mentioning at the beginning. So for example, let's see how we can calculate this activity data. So imagine we have a vehicle stock of cars, for example. So we would multiply this stock by the average distance traveled by each car. By this, we will have the vehicle kilometers. If then we multiply by the occupancy factor of those vehicles, like for example, 2 persons per car, we will have the passenger kilometers. If instead of cars, we are looking at freight transport mode like trucks, we will have the truck stocks multiplied by the average distance of the trucks, and then we will have again vehicle kilometer. If then instead of occupancy factor, we multiply by load factor, which is the number of tons that each truck is carrying, we will have ton kilometers. And this is how we can get some of the activity data for the transport sector. But how can we collect all this energy efficiency data? In 2009, the IEA recognized the value of collecting end-use data, and it started this activity. And thanks to the cooperation with international experts, an Excel template was developed that is currently available online in the IEA website. And with this, we are able to collect both energy consumption and activity data for their sectors: residential, services, industry, and transport. And we publish the energy efficiency indicators database twice per year, in June and in December. And we also published this report, the Energy Efficiency Indicators Highlight, that where we can see the graphs that we create from the data collected for each country and for each sector. So in here, for each country and each sector, we detail some of the more specific aspects, like, for example, the decomposition of each country, the CO2 emissions, the different shares of end use. And here we include all the countries that collaborate with us. So of course, we are open to anyone that would like to collaborate with us. We can see it and have a more detailed look in your particular situation, and maybe make a partial collaboration. But just to say that we are open to include anyone that would like to collaborate with us. Here we can see how the questionnaire actually looks like. As I mentioned before, it's for free in the website. You can download it, and may be useful to see what kind of data we collect, in which units, for which sectors, what activity data, what consumption data. So again, you can have a look at this in the website. Quickly going again through which kind of methodologies can be used to collect this data needed for the development of energy efficiency indicators. Very quick, since I understand you already had a look on the previous presentation. But what I would like to emphasize is that first, before starting any new data collection, it's a good practice to make sure that these data are not already collected somewhere else, right? So having a look at the data available in the administrative sources, it's a good starting point. So for instance, if you need some activity data for the transport sector, is it possible that the Ministry of Transport is already collecting it? If you are sure that these data are not available, you can start your own data collection by, for example, designing a new survey. However, it might be a better and less expensive alternative to add a couple of questions, probably to an existing survey. So for example, if we want to collect some data on transports, and we know there is already a survey for the household sector, we might consider adding a couple of questions regarding how many trips we do per day, how long those trips are, so we can have an idea of the passenger cars consumption, and that would only take us to include 2 extra questions on that survey, rather than starting a survey from scratch, for example. Another option are the measure and metering, that it's relatively costly, but really effective if you want to measure efficiency for specific equipment, for example. And here in this category, we have the use of smart meters, that they are being more and more used, and those kind of equipment. And finally, we have the modeling, that it can be complementary to the other methodologies or standalone. For instance, we can have a model that uses activity data and total energy consumption data from the energy balances as an input to estimate, for example, the end use data in the residential sector. And the IEA developed 2 manuals to help on this work stream of end use data collection and efficiency indicators. And the first one, the Fundamentals on Statistics, focus more on how to collect this end use data and how to develop those efficiency indicators. And the second one, the Essentials for Policymakers, focus more on how to interpret those indicators. And both manuals, you can find them for free online, in English, of course, Spanish, Russian, Chinese, and French. And related to those manuals, you can also find 2 online courses that we encourage you to take in case you want to go deeper in those topics. And here, what we can see is the country practice database. And it's, before starting any data collection, it's always useful to have a look at what other countries have done before. So this is a very powerful tool to consult before starting a new data collection, because you can see what other countries did and take advantage of their experience. For example, if you are planning to develop a new data collection, such as a new household survey, you can come here, check residential, surveying, questionnaire, and you will see even the actual questionnaires that were used by other countries to develop that survey, what was the response rate, what were the learnings from that survey, what were the difficulties of that survey. So it's really useful when we are starting a new data collection. And of course, if you have any country practice that you would like to share, please contact us and we will make sure to make it available for others so others can benefit. Sorry. And finally, I would like to conclude with some key message. And the first of them is that to emphasize the importance of having detailed energy and activity end-use data, which are crucial for effective policies. So these data are essential for identifying priority sectors, understanding energy efficiency trends, and to design and monitor the policies. So therefore, it's extremely important to raise people's awareness of the need of this detailed data and the benefits of country-specific data collections. It's true that they can be costly, but not collecting this data could be even more costly. So most of the times, it's a worth it investment. It's also important to benefit from the experience of other countries and organizations, as like, for example, the country practice database that we just saw, and also contributing to these platforms. And finally, we would like to invite all countries that want to start collaborating with us on end-use data and efficiency indicators to reach out so we can discuss in more detail your particular situation and potentially start a new collaboration with you. So thank you very much for your attention.